Edexcel Core Pure First Order Differential Equations, Modelling with Differential Equations. In mathematics, we often use equations to represent real-world situations, and this process is called modelling. We take the real-world problem and represent it as mathematical equations. If the real-world problem or the mathematical equations involve rates of change, then the mathematical model involves the use of what are called differential equations. And this is where we look at rates at which things are changing. Often, the rate at which something is changing is with respect to time. So for example, velocity is the rate of change of displacement x in terms of time t. So velocity is the rate at which displacement x is changing with respect to time t. So in this case, t would be the independent variable and x is the dependent variable. It's x that is changing with respect to time t. However, we may wish to consider changes with respect to other variables other than time. So for example, the rate of change of volume of a snowball with respect to its surface area would be given by dv by dA, the rate at which the volume is changing with respect to its surface area. Differentiation with respect to x is often represented using a dash, so you may see dy by dx written as y dashed just for a shorthand notation. Likewise, if you wanted the second derivative of y with respect to x, you might see it written as y double dashed. Similarly, a dot can be used to denote differentiation with respect to time. So for example, d2x by dt squared could be represented by x double dot, and dx by dt could be represented by x dot. So in this modelling example, we're going to look at Newton's law of cooling, which states that the rate at which an object is cooling is proportional to the amount by which its temperature exceeds the surrounding temperature. If the room has a constant temperature of 20 degrees Celsius, can we formulate a mathematical model to represent this information? So the first thing we need to do is to define the temperature of the object. So let capital T be the object temperature at time little t. So capital T is the temperature of the object at time little t. The temperature of the object above the room temperature. So what's the difference between the object's temperature and the room temperature is going to be T minus the temperature of the room, which is 20. And now we can start to think about the rate of cooling. So the rate at which the object is cooling. So now we're talking about rates of change. So the rate of change of temperature is going to be capital T by dt for time. And we know that the rate of change of temperature is proportional to the temperature of the object above the room temperature. But we also know that the object is cooling down. So dt by dt I'm going to make minus k t minus 20. So although solving this differential equation is covered in the A-level syllabus, here we are focusing on the modelling and how we've created this first order differential equation using rates of change. So the things to note: clearly define your dependent variable capital T, which is the temperature of the object. Make sure you're aware of the temperature of the object above the room temperature, and capital T by dt is the rate at which the temperature is changing. That needs to be proportional to the difference in the temperature of the object in the room, and to make sure it's clear that it's cooling down, we're going to put minus in front of the K. So the negative sign indicates the temperature is decreasing, and K is now a positive constant. Some questions will involve the use of the chain rule. For example here, the volume V of a spherical balloon is increasing at a rate of 15 centimeters cubed per second. We want to find the rate at which the radius is increasing when the radius is 10 centimeters. So the thing we have here, we are given the rate at which the volume is increasing. We know it's 15 centimeters cubed per second. In other words, the rate of change of volume with respect to time, dV by dt, is 15. And that is a given piece of information. So when you're reading these questions, look for a given rate of change. We're trying to find the rate at which the radius is changing with respect to t. So that's the thing we're trying to find. So always, having read the question, look for the rate of change which you are looking for, and here it's dr by dt. We know also that this is a spherical balloon, so we know that the volume is going to be 4/3 of pi r cubed, and if we differentiate this with respect to r, we get the rate of change of volume with respect to radius is 4 pi r squared. So that's a rate of change that we have calculated from a formula. So these are usually the things we're looking for in a question. Is there a given rate of change? Is there a rate of change which we're trying to find? And is there a rate of change which we can find from a formula? Now we can apply the chain rule. So that would be the rate dV by dt is differentiate v with respect to r times the derivative of r with respect to t. Thing to notice here, to just check you've got everything in the right place, if you imagine these dr's cancelling out, you would be left with a dv on top and a dt underneath. So that's a quick way of checking everything's in the right place. So dv by dt was given as 15. dv by dr is 4 pi r squared using a formula, and dr by dt is the thing we are trying to find. So if we rearrange this now for dr by dt, we get dr by dt is 15 over 4 pi r squared, and often these questions ask you to find a rate of change at a particular instance, and the one we're interested in is when the radius has reached 10 centimeters. It's worth notice, by the way, as the radius gets bigger and bigger, the rate of change of the radius would decrease. So when r equals 10 centimeters, we can find the rate of change of r. The rate of change of r, and that would be inferred as being with respect to time. So that's 15 over 4 times pi times 10 squared, which gives us 0.012 centimeters per second. So there's the rate of change, 0.012 centimeters per second at the instance when the radius is 10 centimeters. So the things to be aware of in the question. Can you see a rate of change which has been given in the question? Which rate of change are you looking for? Is there a rate of change which we can find by differentiating from a formula? And here we have the volume of the sphere. and always check that you get the chain rule in an appropriate form. So for example, the thing to watch out for, if you imagine the drs cancelling there, we'd have a dv on top and a dt underneath, and usually we are looking for a rate of change at a particular instance or a particular fact in the question, and here we're looking at r equals 10 centimeters. In the next video we're going to be looking at the general and particular solutions.